In 2014, like an echo from the depths of space, faint electromagnetic signals from an ancient stellar explosion reached the sensitive camera of the Hubble Space Telescope. 4 barely perceptible points of light, multiple images of the same supernova, were arranged around a distant galaxy whose immense gravitational field had bent their light en route to Earth. After an astonishingly long journey, spanning 9.3 billion years, these images arrived in rapid succession. Yet other, more winding paths had been woven through the fabric of space-time by distortions caused by the surrounding galaxy cluster. Using sophisticated models, astronomers predicted a single reappearance of this explosion the following year. They waited patiently, meticulously preparing Hubble, and precisely 12 months later, the miracle occurred. The delayed afterglow of the supernova appeared exactly as forecast. It is remarkable that humanity could make such a prediction at all. Even more astonishing, however, is its scientific value. In a 1964 paper, Supernova Refsdal proposed that the time delay between gravitationally lensed images of a supernova could serve as a key to measuring the expansion rate of the entire universe. Today, this concept has been successfully realized with the supernova that now bears his name, Refsdal. Moreover, the method has advanced to such a degree that it may become the most powerful tool yet for uncovering the nature of dark energy. Since 1929, the scientific community has known that the universe is expanding. Since 1998, it has been clear that this expansion is accelerating. The cause of this acceleration remains a mystery, hence the provisional term dark energy. The prevailing cosmological model assumes that dark energy has constant density, the amount of repulsive push per unit. Yet recent data suggest otherwise, possibly explaining discrepancies between the main methods used to measure the universe's expansion rate. Let us examine these methods more closely. On one hand, studying the oldest light in the universe, the cosmic microwave background, CMB, provides a detailed snapshot of the cosmos shortly after the Big Bang. Combined with the standard cosmological model, this allows scientists to predict the current expansion rate, quantified by the Hubble constant. On the other hand, observations of supernova explosions trace the expansion history of the relatively recent universe. Type 1a supernovae, thermonuclear explosions of white dwarf stars, have remarkably consistent intrinsic brightness, enabling astronomers to determine their distances based on how dim they appear from Earth. These distances, in turn, yield another measurement of the Hubble constant, offering a more direct probe of the modern expansion rate. If both measurements are accurate and the cosmological model is correct, the CMB and supernova-based values should agree. They do not. Supernova data indicate an expansion rate several percent higher than the CMB-based extrapolation. This implies that either the CMB results, the supernova results, or the cosmological model used to connect them is flawed. This so-called Hubble tension has persisted for years and refuses to vanish, even as measurement precision improves. This suggests that new physics may be required in our cosmological framework. For instance, the current model assumes constant dark energy. But what if dark energy actually evolves over time? Before drawing definitive conclusions, independent measurements of the expansion history are crucial. Supernova results are particularly vulnerable to systematic errors, as they rely on a multi-step distance calibration chain. The more links in this !@meta, pause, sex, 2.0. Some experts, including the author, believe one of the most promising independent approaches is time delay cosmography, a method first proposed by Supernova Refsdal and already applied to the supernova that bears his name. However, an even brighter and more common cosmic phenomenon can also be used: quasars. The most successful time delay cosmography studies to date have indeed used quasars. Thus, our story begins with quasars, but, as we shall see, supernovae also have a significant future in this field. A quasar arises when the supermassive black hole at the center of a galaxy enters an active accretion phase, a periodic occurrence. Active galactic nucleus is the broader term. Quasars are the exceptionally luminous subset of particular interest. As matter falls toward the galactic core, it is captured by the black hole's immense gravity and spirals inward. The gas along this path heats up so intensely that the resulting accretion disk shines brightly enough to be seen across the universe. Quasars are messy eaters. Infalling material arrives in bursts and surges, causing the bright central region to fluctuate dramatically. This makes the entire object flicker on timescales ranging from hours to months. By itself, a quasar is not ideal for distance measurement, but introduce a new layer of cosmic chaos and something extraordinary happens. According to Einstein's theory, light does not travel in straight lines through the universe. Mass warps the fabric of space-time, and light must follow these curves. Gravitational lensing effects are ubiquitous in the cosmos. Most are subtle, slight brightening or distortion of distant objects. But in rare cases, when a gravitational lens aligns with extraordinary precision between an observer and a distant light source, the source, light, we then literally see the same object through different routes in space, producing duplicated images arranged around the lens. This phenomenon, known as strong lensing, turns multiply imaged quasars into potential tools for tracking cosmic expansion. The core idea is straightforward. Light from a quasar, traveling along 2 or 4 different paths, covers different distances, so each image arrives at Earth at a different time. Thus, we observe the same quasar at slightly different moments in its history. This is where the quasar's variability becomes essential. Although its brightness fluctuations appear random, they produce recognizable patterns in its light curve, the graph of brightness over time. By comparing the light curves of the multiple images, astronomers can identify matching features and calculate the time delay between them. This time delay then enables measurement of the actual distances to both the lens and the quasar. This is only a simplified overview. The reality is more intricate. The mathematical foundation rests on Fermat's principle of least time. Light always takes the path between 2 points that requires the least travel time. This principle explains both ordinary optical lenses and gravitational lenses. In gravitational lensing, the paths correspond to local minima in light travel time. If a photon deviated slightly from such a path, it would take longer to reach the observer. The total time delay has 2 components, the geometric path length difference and the Shapiro delay. Extra time incurred as light passes through varying depths of the lens galaxy's gravitational potential. Remarkably, the resulting time delay formula is relatively simple. Crucially, its leading term scales inversely with the Hubble constant, the very quantity we seek to measure. Thus, the time delay provides a direct route to H0. Well, if the method is so elegant, why hasn't it superseded supernovae as the standard for measuring cosmic expansion? Several challenges stand in the way. First, suitable strongly lensed quasars are rare. They require near-perfect alignment between observer, lens, and source. Second, and more critically, most lensing galaxies are difficult to model accurately. Unlike precision ground glass lenses, galaxies are clumpy, irregular collections of stars and dark matter. To compute time delays precisely, we must know the galaxy's gravitational field in detail. Surprisingly, lens modeling is possible at all. A key simplification is the thin lens approximation, Because cosmic distances vastly exceed galaxy sizes, we can treat the lens as a flat mass sheet. This reduces gravitational lensing to a problem in geometric optics. Models are built using the light from the lens galaxies, stars, and the positions of the lensed images. This works well for simple lenses, but such systems are uncommon. Even then, complications remain. We see the stars, but not the dark matter, forcing assumptions about its distribution. Nearby galaxies and large-scale structure also perturb the light paths. Most insidious is the mass sheet degeneracy, the assumption that the lens galaxy alone dominates the deflection, ignores the cumulative effect of other mass layers along the billions of light-years the light traverses. Correcting for these effects is non-trivial. The best way to break these degeneracies is through independent measurements of the lens galaxy's gravitational field. Stars within the galaxy move under mutual gravity, and their motions, detected via averaged Doppler shifts in their light, reveal the true mass distribution. These kinematic measurements yield far more robust models. However, they are observationally demanding, and usually, assuming we have a perfect lens model, how do we measure the time delays? This requires years of monitoring with a large professional telescope to construct light curves for each image. Even this is challenging. The lensed images are often so close together that Earth-based observations blur them together, requiring sophisticated deblending algorithms. Their faintness adds noise to each measurement. Continuous monitoring is impossible. Daily gaps occur due to daylight, and a months-long seasonal gap arises each year when the sun blocks the target. All these factors increase uncertainty when aligning light curves to extract time delays. The combination of observational limitations and lens model uncertainties leads to significant errors in H0 measurements from individual lenses. So, where does the field stand today? In 2019, the H0 Leica collaboration published H0 equals 73.3 plus or minus 1.7 kilometers per second per megaparsec, based on 6 well-studied lensed quasars. Last year, its successor, TD Cosmo, refined the analysis and added 2 more lenses, yielding a slightly lower value of 71.8 plus or minus 2.0. These results align more closely with late universe supernova measurements than with early universe CMB inferences, though their uncertainties remain larger than those from supernovae. On their own, time delay cosmography results do not conclusively confirm the Hubble tension. However, when combined with supernova data, they significantly strengthen the discrepancy, suggesting less than a 1 in 10 million chance that the difference is due to random noise. Still, the tension isn't definitively proven. An unknown systematic error could be biasing the supernova result upward relative to the CMB. In that case, current lensing measurements aren't yet precise enough to settle the issue. What lies ahead? Quasars are ideal for this work. They are extraordinarily numerous across the cosmos. But time delay cosmography, how do they fare? The precise measurement of the time delay for the late arriving 5th image of Supernova Refsdal yielded an H0 estimate of approximately 70, but with substantial uncertainties. There is also the lensed supernova SNH0PE, which is particularly notable because it belongs to the same Type 1a category used in other measurements of the Hubble constant in the late universe. In a sense, this single object has provided us with 2 independent measurements of H0. In practice, these were combined. The lensing component yielded a fairly direct estimate of H0, while the Type 1a supernova analysis helped resolve certain degeneracies inherent in the lensing model. The resulting Hubble constant from H0PE aligns with other measurements of the modern universe's expansion rate, though, once again, with very large uncertainties. For both of these supernovae, the uncertainties are substantial, but not significantly greater than those obtained from any individual lensed quasar. The advantage of quasars lies in their sheer numbers. statistical aggregation allows us to reduce overall uncertainty, ultimately increasing the sample sizes of both lensed quasars and lensed supernovae will be key to further progress, and this breakthrough is imminent. In early 2026, the Vera C. Rubin Observatory will commence its Legacy Survey of Space and Time, LSST, repeatedly imaging the entire southern sky every few nights for a full decade. Combined with other new facilities, such as the European Space Agency's Euclid satellite, we anticipate the discovery of thousands of new lensed quasars and hundreds of lensed supernovae. Estimates suggest this will reduce the uncertainty in H0 to 1% or less, which, if achieved, would render the Hubble tension undeniable. Yet the Rubin Observatory promises, with a sufficiently large sample of lensed quasars and supernovae, we could not only measure the current expansion rate, but also reconstruct how the expansion history has evolved over cosmic time. In the current standard cosmological model, lambda CDM, dark energy is assumed to have a constant density. However, compelling evidence, mentioned earlier, challenges this assumption. In 2025, the Dark Energy Spectroscopic Instrument DESI collaboration released findings on the evolution of cosmic expansion using baryon acoustic oscillations. These results, widely publicized, strongly suggest that dark energy has weakened over time. This development is, without exaggeration, the most significant breakthrough in dark energy research this decade. If this temporal variation can be measured with sufficient precision, we may finally begin to uncover the physical nature of dark energy and determine what this mysterious substance truly is. Time delay cosmography via gravitational lensing could prove pivotal in this quest. Indeed, it may become the most impactful scientific outcome of the Rubin LSST project, and many researchers are already actively pursuing this path. At its core, this endeavor amounts to capturing the faint echoes of thousands of ancient cosmic cataclysms, and through them, identifying the true driver behind the accelerating expansion of our space-time.